So let's look at a few example problems that use the two new theorems that we just learned, which was ASA and AAS. And these two theorems, remember, they are able to be used to prove that two triangles are congruent. ASA says that if we have two pairs of angles and the included side between the triangles, then the triangles are congruent. AAS is two pairs of angles and then a side that's not between them, or a non-included side, are congruent, and that makes the triangles congruent. So in example 1, we actually have three triangles, and we're trying to decide, is triangle JKL congruent to either of the other two? Is it congruent to triangle MNO? And then is it congruent to triangle PQR? And so if we look at these triangles, they've already marked everything that's congruent for us. Angle J is congruent to angle M, and angle K is congruent to angle N, and then segment JK is congruent to segment MN, if we're just comparing these two triangles. And so I can see that I do have two pairs of angles and one pair of sides. So maybe one of these two things will work. I'm just going to ask myself, where is that side pair located? Is it between the angles? Well, yes, right? Segment JK, this side is between angle J and angle K. It's included between them. It's connecting J to K, the vertices of the two angles that are congruent to these two angles. And then segment MN is doing the same thing. It's connecting point M to point N. Those are the vertices of the two angles that are congruent to these guys. So for A, I'm going to be able to say, yes, triangle JKL is congruent to triangle MNO. And let's make sure those names are in the right order. JKL goes 1 mark, 2 marks, and then no marks for the angles. MNO does the same thing. 1 mark, 2 marks, and then no marks. Okay, so those letters are in the right order for that congruent statement. And we're going to say they're congruent by ASA. And now we're going to compare triangle JKL to triangle PQR. And are they congruent? And this one can be a little bit tricky for people sometimes, because I do see that they have three pairs of parts congruent. Angle J is congruent to angle P, angle K is congruent to angle Q, and segment JK, it says, is congruent to segment RQ. It doesn't look congruent. This one definitely looks shorter, but we're going to trust in the markings, right? Pictures aren't always drawn to scale. So I have my two pairs of angles and my pair of sides, and over here it's the included side, but over here it's the non-included side, right? And so that actually means that neither one of our two theorems that we learned in this section are going to apply, because we have to have, if we're going to use ASA, the pair of sides that's congruent has to be included between the angles for both triangles. Or if we're going to use AAS, it has to be a non-included side for both triangles. In here it's like 1 and 1. One we have the side included, one we have the side non-included. So for this one, I'm going to say no, cannot determine if the triangles are congruent. Right? We don't have ASA or AAS for both of them. Alright, so example 2 then says, state whether each pair of triangles is congruent by SSS, SAS, ASA, or AAS, or if the congruence cannot be determined. Right? These are the four things that we can use now to determine triangles congruent. Remember, the order matters on these. So for SAS, the angle is the included angle between the sides, and then ASA, AAS, like I talked about before. Okay, so example 2, we have 4 different pairs of triangles that we're going to try and look at. For A, you can notice I have an angle and an angle, an angle and an angle, so I have 2 pairs of angles, and I have a pair of sides that's between them. Included side, included side. So for this one, I'm going to say, yes, ASA works, but I'm also going to say AAS works, and the reason is, from that third angle theorem that we've talked about a little bit, this angle must also be congruent to that angle, because if 2 angles in this triangle are congruent to 2 angles in this triangle, then the third angles have to be congruent so that they would all add up to 180 in both triangles. And then we could look and see, oh, this angle congruent to that angle, this angle congruent to that angle, and then this non-included side congruent to this non-included side, that's AAS. Which means, by the way, that pretty much every time ASA works, AAS will also work, and vice versa. Just keep that in mind. If I look at B, it's pretty straightforward on this one. All I see are a bunch of sides congruent, no angle marks in these two pictures. and it's all three sides of this one, congruent to all three sides of this one. So that one should be pretty straightforward. It's SSS. Example C here, we have an angle congruent to an angle, another angle congruent to another angle, and then a pair of sides congruent. If I look at that, in this triangle it's a non-included side, not between these two. And in this triangle it's the non-included side. And interesting to note, important to note, it's across from the same angle in both triangles. The side that's marked congruent is across from the angle that has two arc marks on it. So that means that we have two pairs of angles in a non-included side. So AAS works. Like I explained earlier, that would mean that ASA would also technically work because this angle and this angle must be congruent, and now the side is included between these two angles. This side is included between the same two angles on the other triangle, so ASA will also work. D, I see a pair of sides congruent here, another pair of sides congruent here, and then a pair of angles congruent here. So with two sides and one pair of angles, my attention would be going to SAS and asking myself, does that work? And the important thing, remember, is the angle must be included between the two sides, like it is here. Angle included between these two sides is the angle that's formed by these two sides kind of meeting right here at this vertex. But over here, that angle is not in the right spot. It's not the included angle between these two sides. These two sides that are marked congruent, they meet right here. This would be the included angle for them, and it's not marked congruent to this one, and there's no reason to think that it is congruent. So for this one, I'm going to have to say congruence cannot be determined. Maybe these two triangles are congruent, but we can't say for certain right now. Alright, one last example here. Find the value of x. And so we can see we have a couple triangles with some actual measurements here, not just markings, but 9 feet and 9 feet, 87 degrees, 87 degrees, 40 degrees, 40 degrees, 7 feet here, and then an algebraic expression for the length of AB, x plus 4 feet. So what's going on in this picture? Well, we can see that these angles here and here are congruent to each other. 87 and 87, that means they're congruent. 40 degrees, 40 degrees, they're congruent. And then segment PR is congruent to segment AC. So triangle ABC must be congruent to triangle PQR by angle, angle, side, according to this picture. If those triangles are congruent, then the length of AB, so the distance from A to B, must be equal to the distance from P to Q because of something we learned in a previous section. The corresponding parts of congruent triangles must be congruent. Segment AB and segment PQ are corresponding parts. They must be congruent according to CPCTC. So their distances must be equal. So if I take x plus 4 for segment AB, it needs to equal 7 for which is what the length of segment PQ is. And then we can just subtract 4 from both sides of this equation, and that x value must be 3.